Okay, good morning everybody. So today we're going to start with chapter 2. And it is about elements and compounds. We're going to learn how to make ionic and covalent compounds. But as a start, we're going to do kind of a revision about the structure of the atom. So the atom is consisted of a nucleus, and around it there is an electronic cloud. Electrons around the nucleus. The nucleus have two particles, protons and neutrons. Now, usually the protons are positively charged. The neutrons are in neutral. The electrons are negatively charged. Now, the picture that we have in here, or the schematic diagram that we have in here, is not to scale. What does that mean? That in real life, the atom, if we have the nucleus, you have to imagine the nucleus being a rice, a small rice, that's the nucleus, and imagine the stadium. Imagine that we put that rice in the middle of the stadium. The nucleus is that small, and the atom is that big. As much as the stadium and the nucleus is the smallest part of it, and it is in the middle of the stadium. So mostly, if we're going to look to the atom is mostly space, with a very heavy center, which is the nucleus in there. Now, the electrons, the protons usually are positively charged, and their mass is 1.672623 times 10 to the minus 24 grams. That's a very, very tiny, small mass. And usually we represent it as 1.007 atomic mass unit. Usually you see it as unit U, or in old references as AMU. So whether you saw 1 AMU or 1 U, that means mass unit. And we're going to talk about the conversion. How much is a 1 mass unit? As it is clear, it's almost 1.726 times 10 to the minus 24 grams, because we said that this is the mass of the proton in gram, and this is in atomic mass unit. The electron is negatively charged. The mass of the electron is 0.0005 mass unit. This is why usually the mass of the atom is coming from the proton and the neutron. Why? Because the mass of the electrons is so tiny that it is negligible compared to the mass of the proton and the mass of the neutron. Now, the neutron has no electric charge, as we just said, and its mass is very close to the mass of the proton, and it is equal 1 mass unit. In other words, the mass of the atom is coming from the nucleus. It's not coming from the electrons around it, because the electrons around it, they are very tiny in mass compared to the nucleus. So a 1 AMU, or atomic mass unit, or U, equal to 1.661 times 10 to the minus 24 grams. This is the conversion. It's the same as when I say a 1 kilogram equal 1,000 grams. A 1 AMU equal 1.661 times 10 to the minus 24 grams. Do you need to memorize this one? No. Do you need to know this number? Usually, if you're asking where did they get this number from, this is 1 over 12, the mass of 1 atom of carbon 12. This is where we get this conversion from. And this is a convention. It's just the scientist said, okay, I wanted a 1 AMU, or a 1 atomic mass unit, to be equal to 1/12 of the mass of the carbon, of 1 atom of carbon. This is where this conversion comes from. Now, how we usually represent elements, as you can see, there are a lot of elements in the periodic table. Usually we give them a symbol, and you need to know the names, because in exams I'm going to provide you with a periodic table, more or less looks like this periodic table in here. It's going to have all the numbers, but only the symbols. So you have to get used When I say C, that this is carbon. When I say B, when I boron, N, nitrogen, O, oxygen. So the way that usually chemists do it is they take either the first letter of the name of the element as the symbol, or the first two letters. For example, in case of calcium, we already have carbon that have the first letter as its symbol. This is why we take here the first two letters as Ca as the symbol. Because we have boron and we have beryllium, so we take Be as the first, as the symbol of that element. The same for neon, because we have nitrogen, so we put Ne. Silicon, Si. Now what if we have three elements that have that their names start with a C, like carbon, calcium, and chromium? So usually we abbreviate it, or the symbol that we use is the first and the third letter. Okay? Now the way to learn that is just to get the periodic table with the names on it, and I think I'll have that, and just try to remember what is what. Okay, chromium, Cr. Boron, B. Now some of the elements in the periodic table, the name doesn't match, like the symbol has nothing to do with the name. The examples are mercury, Hg, that has nothing, the symbol has nothing to do with the name. Tungsten, W, tin, Fn, iron, Fe. Okay? Those are some of the exceptions that the symbol does not. It's not the first letter, it's not the first two letters, it's not the first and third letter. Okay? Now, definitely we need to understand, when I give you a periodic table, you need to understand what all these numbers and signs that are in the periodic table. Usually you're going to see something, a letter here, then two numbers, A and Z. Now this one, this is the elemental symbol. We just talked about that. It can be either the first letter, the first and second letter, the first, third letter, or nothing to do with the name. Okay? This is the elemental symbol. Z is the atomic number, and it is equal to the numbers of protons. So Z is equal to the atomic number, and it is equal to the number of protons. Now A, it is the atomic mass, and usually it's represented in mass unit, average atomic mass, and A equal to the mass of the protons plus the mass of the neutrons. So it is the atomic mass. It is the mass of the neutrons and the protons, because we said that the mass of the electrons is negligible and we don't consider it. But in most of the references, what you see that A equal to the number of protons plus the number of neutrons. I think most of you seen that in high school. So what is that right? Is it right to say that A is the number of protons plus neutrons? No. It is no, and it is yes. Remember that the number of the mass of the proton equal 1.007 unit, right? And the mass of the neutron is 1.009 unit. So it's approximately, the mass of the proton is approximately 1. The mass of the neutron is approximately 1. So if I have 10 neutrons, their mass will be 10.00 something unit. 10 protons, approximately 10.00. This is why sometimes they teach you in high school that A equals the number of neutrons plus the protons, and it is kind of a valid, approximately a valid assumption, yet mainly this is equal the mass of the proton plus the mass of the neutron. And usually this is what we're going to do from now on. I know the number of protons. If this is the number of protons, we can consider A approximately to be the number of protons plus the neutrons. So if I want to know the number of neutrons, I just A minus Z is the number of neutrons. Okay? But you need to know that this is that A equals the number of neutron plus proton is an approximation, and it isn't exactly the same. And we're going to learn today that this A is an average of more than one isotope, and that makes the approximation even a little bit far than reality. Now, Usually we will see a lot of periodic tables out there. Some of them, they will have A on top, like A, which is the atomic mass on top, and Z on the bottom, atomic number. Some others, they will shift, they will do it the other way around. How you gonna know which is which? Even whatever is a periodic table, how you gonna know which is which? Yes? Very good. The smaller one is always the atomic number. It doesn't matter what kind of periodic table I provide you here or when you go out of this class to anywhere. Yes, periodic tables kind of they represent it in different way. Always the atomic number, which is the number of protons, gonna be smaller than the atomic than the atomic mass or mass number. This is also known as mass number. So this is how you read whenever I give you a periodic table. I'm giving you a lot of information. I'm giving you the symbol, I'm giving you the atomic mass, I'm giving you the number of protons. Okay? Now, in a neutral atom, like anything from this periodic table, and I mean by neutral that it isn't charged. It isn't X minus or X plus or X2 minus or X2 plus. This is a charged atom, which we're going to call cations and anions today. Sometime today we're going to learn that. Now, in a neutral atom X, as it is, the number of protons equal to the number of electrons. And this is why it is a neutral. Because the proton have a positive charge, the electron have a negative charge. So if I have equal amounts of neutrons and the proton, the element will be neutral. Because there is a balance between the plus in the nucleus and the minus around it. This is why the element is a neutral. Okay? Now, any imbalance in that is going to make it a charged element. So for a neutral element, the number of a neutron must be equal to the number of electrons. Otherwise, it will be charged because there will be imbalance. Either you have more protons or more electrons there. Make sense? Good. Now, again, what I'm trying to point out in here is the idea that I just mentioned. The idea that sometimes they put A on top, Z down, or Z on top and A down. An example of that here, I'm just trying to show you that manganese have a 25 and 54.938 as an atomic mass, and the question is calculate how many protons does it have. So this is the number of protons, 25 is the number of protons. The mass, the atomic mass is approximately equal to the number of protons plus the number of neutrons. So if I want to calculate the number of neutrons, it is that atomic mass minus 25, which is the number of protons. Okay? Which is around 20. Now, I think that's simple, so let's do an ITK test to make sure you get the idea to go through. And I'm going to stop it at 1. Okay. I'm going to stop it and check what is that. So I have one at 92%, and that's right. 1 is the right answer. So this is the number of protons. This is the atomic mass, or as an approximation equals the number of neutrons plus the protons. So 127 minus 53, that's going to be the number of neutrons. And that brings us to 5374 as number of, how many electrons and neutrons? So we know that the number of protons equal to the number of electrons, so 53, and the number of neutrons is 74, which is the difference between those two numbers. Okay, let's do this one. It's going to be A, B, C, D, so refresh your iClicker because it's still a 1, 2, 3 system. So which of the following atoms contain the largest number of protons? Again, I'm going to stop it at 1 minute. There is no C. Oh, okay, just vote as A, B, D, E. Okay, sorry, I apologize. By the way, even if you send C, you can correct it by sending it one more time. Usually the computer always gonna, it records the last answer you did press. Okay? Okay, I'm gonna stop in here and check what you think. Very good, 98% think C, and D is the right answer. So the number, and the whole idea about this question is to not to mix between the number of protons and neutrons and electrons. You will find much more about this to practice these on our, so practice more about neutrons, protons, electrons, and all of these on our. Now, usually, for example, for almost every element in the periodic table, in nature, on Earth, we find for each one a sister. We call it a sister. This is not the chemistry name. This is what I call it. A sister. That sister of that element, it have exactly the same number of protons. That means the same V there, but they have different mass. They have different number of neutrons. An example of that is hydrogen. Hydrogen has two other sisters, which we call isotopes. An isotope is the element, it's the same element. Isotopes are the same elements, it have the same number of protons, but they differ in the number of neutrons, or the A up there. Okay? We wake up in this Earth, and we find all different kinds almost for each element. We find different isotopes. It's exactly the same element, so it has exactly the same proton. The three of them, they must have the same number in here, and they only differ, same number of protons, and different number of neutrons. And we call these isotopes. And these isotopes, they have different percentage of abundance. And we mean by percentage of abundance, that means if I go now in this universe, collect some hydrogen and do some kind of mass spec to figure out how many of them they weigh just 1 AMU, how much of them they weigh 2 AMU, and how much 3 AMU, I'll find 99.985% they weigh 1 AMU. And 0.0115 they weigh 2 AMU, and the traces, which is the addition of those minus 100 to be with 3 AMU. Okay, so and this part, which is the isotopes, is very important for later on when you go to organochemistry, and they have a very, they are well used in chemistry for a lot of stuff, and even in imaging, in cancer treatments, usually, especially the radioactive isotopes. The isotopes of those that are radioactive are the ones that are used in cancer treatment, in medical imaging, and a lot of other stuff. Even we use it in research, in chemistry research, to trace the mechanism, to know what's going on. Now, another example of isotopes is carbon isotope. It has another isotope which has 14 as a mass, as atomic mass unit. This is the most abundant one. Also oxygen, it has oxygen 15 and oxygen 16, bromine 79 and 81. Some of them, they have 3, 4 isotopes. At this stage, you don't have to know. In the question, I'll provide you how many isotopes does it have and how much is the abundance. Definitely, you don't need to memorize the abundance. I'll provide you with that in exams and even, yeah. How do you know? Very good question. And that's gonna, first of all, definitely you need to do analysis. That means we do chemistry analysis. We take, for example, carbon. We take, for example, any carbon from this earth, and we do mass spec, and we found how much weight, for example, 16, 14, how much they weigh 16. And this is how we know the abundance. Okay? Usually those percentage abundance, they are usually calculated. There are tables that are published out there by National Institute of Science and Technology. They are called NIST catalogs. You can just open it and find the abundant thing. Okay? Now, before we go any, let's cover this. Okay, which of the following are isotopes? A, B, C, D, A. We have the C. 98% B. What a great class. Okay, this question is exactly from spring. Last spring, I gave exactly this question in the exam, and I had a 20% of the students voting to something else. Okay, so the most important thing when we're talking about isotopes is to look that it is exactly the same element. So you can't say that those are isotopes. They aren't isotopes. They are using the same element. It must be the same element to consider it an isotope. Then we have to look whether the number of neutrons is the same or different. Okay? Now, we thought that we have more than one element out there, sister isotopes. Now, if we look to the periodic table, like an example in here, if you look to the mass of hydrogen, it is 1.00794. And we said that we have hydrogen 1, hydrogen 2, and hydrogen 3. So the mass that is recorded right there, which is the atomic mass that we just talked about, is the average atomic mass. What does that mean, average? Because I have, on this earth, I have hydrogen 1, which is its mass is 1, and I have hydrogen 2, which has a mass of 2, and hydrogen 3, which has a mass of 3. What we record in the periodic table is the average of those 3 masses. But definitely, we're gonna take into consideration the abundance, how much I have of each isotope. And this is how we calculate the average atomic mass. So the average atomic mass of any element is the percentage abundance of isotope 1. If we're talking about hydrogen, it's going to be hydrogen 1. And this question mark must be multiplied. I don't know why my PowerPoint put it as question mark. Multiplied by the mass of isotope 1 plus the percentage abundance of isotope 2, in this case it's H2, multiplied by the mass of H2 plus the percentage abundance, definitely over 100, each one of those over 100, plus the abundance of the isotope 3 over 100 plus mass. What if I have only 2 isotopes? It's going to be just the percentage abundance times mass isotope 1 plus percentage abundance mass 2. If I have 5, I'm going to put 5 terms of that. Get the idea, guys? Okay, very good. An example of that is a chlorine. It has 2 isotopes, which is chlorine 35 and chlorine 37. The exact masses are here for both of those, and I have the percentage abundance. I'm going to calculate the average atomic mass. So the average atomic mass of chlorine equal to the percentage abundance of chlorine 35 over 100 multiplied by the mass of chlorine 35 plus the percentage abundance of chlorine 37 over 100 multiplied by the mass of chlorine 37. So if I do plug the numbers, the answer is going to be 35.45 atomic mass here. And I just want to comment on that number, the 35.45. If we look to the mass of the most abundant chlorine, which is 34.9, definitely some other number there, and the 37. The average atomic mass is always closer to the isotope which is more abundant. Does that make sense? Can everybody see that? That always the average atomic mass is going to be close to that isotope, which is to the mass of the isotope which is most abundant. Can everybody see that? This is a 35.45. It's closer to 34.9, which is approximately 35, than 36, which is approximately 37. Okay? This is always the case. The most abundant, the average atomic mass is going to be closer to the most abundant isotope mass. Okay, what about we do this? I'm going to give you 2 minutes because it has a little bit of calculation. Do you need a little bit more time? Okay, so we'll stop it at maybe 3 minutes, because only 56 students answered. 10. Okay, so let's see. I have 79% as C, and C is the right answer. But let's see how. How C is the right answer. So, first of all, it's telling me there is two isotopes for European, and that the average atomic mass, so the average atomic mass, I'm going to abbreviate it as AAM, equal to 151.965U. The percentage abundance of EU1, I'm going to call it EU1, is 47.8. Therefore, the percentage abundance of EU2, since we have only two isotopes, is 100 minus 47.8%. Okay? And that's equal, 1 minus equal to E2.2%. Okay? Now, I know the equation is that the average atomic mass equals the percentage abundance 1 over 100 multiplied by the mass of EU1 plus the percentage abundance of 2 over 100 multiplied by the mass of EU2. And then plug in the numbers in the equation. 965U 0.478 multiplied by the mass that is provided, which is for European one, which is all of this, 9194 plus, okay, 0.522, and I'm looking for X, which is the mass, or the mass of Europe, times the mass of EU2, so this is what I'm looking for. Okay? So it's one equation, one unknown. If you don't know how to solve that, go back to the algebra. You have to the basic algebra. And the right mass is going to be 152.9. So this is how we calculate the average atomic mass, or we can also calculate the mass of one of the isotopes using this equation. Now, if there is 3 isotopes, definitely the equation is going to involve the 3 of them, 4 is going to involve 4 of them. Now, as we look to the periodic table, have you ever asked yourself, how did they put this periodic table together? Have you asked yourself this question, how chemists came to just add it together and put it in this way? So the idea goes back to Mendeleev, and he finished his degree. He did a postdoc, and he was looking for a job. At that period of time, he had nothing to do, and he was kind of looking to those elements within his time for searching a job. And when he began putting the elements according to their atomic number, these days they change it from atomic number to atomic mass because they find it more better. So in the old days, in the time that he put it, it was according to the atomic numbers. Not anymore. Now it is according to the atomic mass. He found that if he arranged them that way, he's finding kind of a correlation in the periodic table. What do I mean by correlation? He found that when he put them this way, that those that belong to the same column, they have most of them, they have almost the same chemical. Most of their chemical and physical properties are the same. Okay? So, for example, in group, and I just want to tell you that we have for these two, group 1, group 2, and all of these are called the main elements. The main elements. All of these groups are the main elements. And then here we call them the transition elements. So, in chemistry, when we say a group, we mean the column. So each column of that is called a group. the row is a period. So if I say group 1 period 1, I mean this, group 1 period 1. Okay? Now, these are the main elements and the transition elements. So when he put them together according to the atomic number at his age, he found that all of group 1, all of these groups are metals except hydrogen. And those are metals. And what he found that as he's going from the left to the right, that they are going less metallic. The elements are getting less metallic. All of these blue, definitely this is color coded as you can see. All of the blue are metals. Those in green are metalloid. That means they have partial properties of a metal, partial properties of a non-metal. And then those in here, which are in this color, they are non-metals. This is what he found. And this is what's great about this periodic table, is that we can talk, oh, all group 1 do this, all group 2 do that, all group 5 does this. And this is what we're gonna talk about in a minute. So here is another periodic table. Yes, this is a more color-coded one. Okay, so let's start with group 1. So all of the elements of group 1 are metals, except hydrogen. It isn't a metal. And the nice thing about all of these that they violently react with water. And I'm going to show you how violent they are. Okay?
And you may, under very strict scientific control, have witnessed potassium mixed with water.
So this is potassium in water.
Odds are, if you have, it will only ever be on one of those rubbish science videos. There you go, mate. Present.
So what he's doing, he's going through group 1 and adding each one. He started with sodium, now he's going to do the potassium.
They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
So the rubidium is in a lower period.
But it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone.
Here we go. This is how violently they react with water, all group 1. And as you see, as you're going down the group, they react more violently with water. So these are called the alkali metals. Group 1 are called the alkali. Then we have the alkaline metals, which is group 2. Then in group 3, so group 1 and group 2, all of them are metals except hydrogen. Now when we go to group 3A, and I'm going to pause a little bit on the way that we name these groups. So there are 2 ways to name the groups. Either 1A, I think you can see in here, 1A, 2A, then suddenly we forget about all the transition metal and jump to 3A, and we name it 3A, 4A, 5A, 6A, 7A, 8A. So this is the way of nomenclature that they take all the main group as called A, then they go back to the transition metal and they call them 3B, 4B, 5B, 6B, 7B, 8B. Okay, can you see this nomenclature? Another nomenclature that you might see and we should be familiar with is they call it 1, 2, 3, and they consider 3 being the transition metal group, 4, 5, 6, 7, 11, 12. Then group 3A, they're going to refer to it as 13 because they consider the transition metal within. And these are 2 different nomenclature, one American, one European. you have to get used to both of them because you're gonna see it here and there. It depends where exactly you're reading, especially if you're gonna later on be working with papers and things like that. It's gonna be either or. Okay, so mostly I'm gonna refer them to use the American system, which is 1A, 2A, 3A, 4A, 5A, rather than the European one. So this is a group 3A. All of them are metals except boron. It is a metalloid. That means have properties of that. Now all of you know aluminum and aluminum from aluminum foil. The other thing about aluminum that all gems are made from aluminum oxide, Al2O3, and all of them they should be glassy in color, the glass transparent. Yet the colors of the gem doesn't come from aluminum oxide. It comes from the transition elements ions like chromium 3+. It gives a color, a very nice color. For example, iron 3. Manganese 2+. It's going to give that kind of the green color inside the gems. So all the gems are made, gemstones are made of aluminum oxide, yet they have impurities which are from the transition elements, and those impurities are the ones that give you the different colors of them. Now for group 4A, the first one, the first element, which is carbon, it's a non-metal, it's not metallic, yet it is one of the most important elements in the periodic table. Why? Because all our body is made of carbon, or organic compounds. Not carbon as it is, but in organic compounds, proteins are made of carbon, DNA have carbon there, so all like living matters are made of carbon, or have partially made of carbon. It is one of the most important elements. This is why we have organic courses which talk about compounds of carbons and hydrogen and oxygen. Most of the time you'll be required to take Orgo 1 and Orgo 2 if you're a pre-med, in a pre-med kind of. We have silicon and germanium. Both of those are metalloids, and whatever is left in that one are metals. Now, we have in 5A nitrogen. Usually it exists as N2, and sometimes we have it in the liquid form. Probably by Monday we're going to do a demonstration about nitrogen. We don't have the liquid nitrogen today, but we can have it on Monday. Those two are non-metals, those are metalloids, and these are the metals. As you can see, those 7A, as it is mentioned in here, the red color, they are called the halogens. And from now on, we're going to refer them to as the halogens. Usually, they exist as F2, Cl2. I mean, they exist in nature in their diatomic form. And it is F2, Cl2, Br2, I2. F2 is a gas. F2, when it is in nature, is a gas. Cl2 is a gas. Br2 is a liquid. I2 is a solid. And lastly, we're going to end with group AA, which they are called, as you can see here, noble gases. And from the name, they are noble. These group number 8, they don't do reaction. Why? Because they are certified. We're going to talk in chapter 3 and chapter 6 why they are happy, why they are the noble, why they are. We still have 2-3 minutes. Okay, guys? Okay? We still have 2-3 minutes. Okay, the noble gases, those gases usually, as you said, as I said, they are noble. They rarely react. We're going to see only one exception of that. Let me see. So, 40 seconds. Okay, now we also have, as you can see here, 2 stars. A star and 2 stars in here. And then we have two rows in there. Those are the lanthanides and actinides. Okay, and if you look to the number, they should be in between 57 and 71 between those, but they are usually represented down there. And because some of them, they are synthetic that recently either we discovered them or found them. In this course, we're not going to talk about the lanthanides and actinides, but maybe a few, but none of you are chemistry major. If you're chemistry major, you're gonna hear about them. Okay? Enjoy your weekend, and I'll see you on Monday. Remember that we have an assignment to do.